Hello my dear students, welcome back to the channel. So before I move on to today's session, I have a very pleasant surprise to share with all of you. This is regarding our 90-day crash course which will cater both of your requirements of Comet K and KCET. Okay, now if you want to ask me right now why this requirement, sir, because it is very it's very high time to decide to make a right decision, because your midterms are around the corner. Okay, you don't have much time to spend and waste on whatever you're doing right now. You have to take a decision. If you want to get enrolled into top colleges of Karnataka, the only way to do it is through KCET and Comet K, and for that we have brought a 90 days offline crash course. You heard me right, offline crash course, which has been conducted across campuses of Diksha. Okay, so what you have to do right now is basically call on this number, get to know which of the campus in Bangalore is nearest to you, nearest to your home, which you can comfortably go to that campus, and more details about the course, when it is conducted, the timings and the schedule. Okay, and get this crash course if you really want to score top 1000 rank in Comet K and KCET and get that dream college of yours and be an engineer. Okay, so right now what you have to do, call on this number, get to know which of the campus is nearest to you, and get the enrollment done, get the registration done, because it is time to take decisions, and let's start taking the right ones from today. Okay, so let's start the session right now. We are clear with what is KC90. KC90 is a 90-day crash course which will cater two examinations, KCET and Comet K. And what is the goal? Goal is very simple, top 1000 rank. Goal is very simple, to get the top engineering colleges across Karnataka. How to do it? Just call on this number and get to know the nearest campus, because yes, this is conducted offline at Diksha campuses. Okay, so you have to know which of the campus is nearest to you, then only you can get enrolled, right? Okay, so make the call, take the right decision. Let's start the session right now. Yes, so it's now time for our rapid revision. Okay, so welcome to the session. We are here completing our chapter application of derivative in one shot. So we'll have two parts of this coming. First part will be the rapid revision, as you can see on the screen, and second part would be where we're going to solve all the most expected questions, whether it is one marker, whether it is MCQ side, whether it is assertion reason, or fill in the blanks, or subjective questions. So we'll see that category as a second part. Okay, so clear, this session is about rapid revision of all the concepts coming in the chapter of application of derivative, starting with the first concept, which is rate of change of quantities. Now usually the questions in this are most likely to come from rate of change of volume of any spherical figure which is given to you, like spherical, whether it is a balloon or it's a bubble, whatever it is. Okay, the ripple question which is there in the let's say you have thrown a there's a ripple created because of you throwing a stone in the lake or a pond, and the ripple is increasing, the radius is increasing there. So those kind of questions can also be asked from the rate of change. Then we have velocity concepts in the rate of change. Then we have some questions on marginal revenue. So all those categories comes under rate of change of quantities only. Just be careful what are they asking you to differentiate, or the change with respect to what variable is introduced over there. So you have to be very careful with that. Change with respect to which variable, that is the most important part. Okay, so in this case, what is this called as? I hope you know this. Delta y by delta x means, this means what? This means that change in y with respect to change in x. So whatever happens to y whenever you make a small change in x is called as delta y by delta x. This is actually referred to as usually average rate of change. Average rate of change. But when you consider, when you make this delta x very small, okay, to basically dx, whenever this delta x is very small, okay, basically delta x tends to 0. Delta x tends to 0 when we use the concept of dx over here, and this whole thing transform into dy by dx. If you remember, this is nothing but your first derivative. Okay, so this is going to be your instantaneous rate of change. This is average rate of change, and this will become what? Instantaneous rate of change. And this part here we study with respect to what? With respect to the derivatives. Okay, the instantaneous rate of change is studied in the derivatives. I'll show you an example of this with the help of velocity and displacement. Remember, we have learnt in our earlier in the physics part as well, you must have learnt average velocity. How do you find that? So if you have a curve like this, you identify 2 points. This is dt curve or displacement time curve, ST we write sometimes. So dt curve, we identify 2 points, we draw the line between them. What do you get? You get a chord there, right, for the given function. You mention these 2 points, you have both coordinates in x and y. This is your y2, this is your y1, this is your x2, x1, okay. And when you find the ratio of this y2 minus y1 upon x2 minus x1, this is nothing but your delta y upon delta x. This is your delta y upon delta x. If you remember, this is called as slope of that given chord. This is the slope of that given chord. If I name it to be, let's say, A here and B here. For the AB chord, the slope is given by delta y by delta x, y2 minus y1 upon x2 minus x1. What is this representing over here? This is representing average velocity. This is representing here average velocity. This is going to be V average wala concept. V average. Got it? This is your V average. But what happens if I make this instant? Right now, what is the time here? This is dt curve, right? The time is x2 minus x1. Right now, this is our time instant, right? This is our time t. x2 minus x1 is the time. But what if we make this time to be very small amount of time? That instant if we make, okay, then this curve over here becomes a tangent. Then it becomes a tangent at this point, at that instant. Okay, then this chord becomes the tangent at that instant, and then the concept becomes from V average to V instantaneous. So whenever you make delta x goes to 0, what it implies? It implies you're talking about not any time anymore. It has become an instant, and at that instant the V average will not be calculated. You'll end up with V instantaneous, and you find this using dy by dx or dt, whatever you want to call, dy by dx or ds by dt. That is your V instantaneous. Okay, so this is the same concept that we use in the velocity. This is clear, right? The rate of change is used in velocity and acceleration. So please check carefully. If you have s, what is s? The displacement function in terms of course the variable t, then your velocity function will be given by derivative of the displacement function. Derivative of the displacement function, which is given as ds by dt. If you're looking for acceleration, you're going to find the derivative of velocity function now. Your a will be derivative of velocity function now. Okay, so either the first derivative of velocity function or the second derivative of displacement function is your acceleration function, right? And if you differentiate one more time, you get something called as jerk, which is nothing but sudden change in acceleration. Sudden change in acceleration is called as quantity jerk. Okay, J-E-R-K. All right, so this can happen, right? If you have sat in the car or you've been driving, when let's say you're already accelerating, okay, you're increasing speed, but again you want to go at a higher speed. What do? You further press the accelerator, your speed again increases. So what happens to your body? You feel the jerk, right? Okay, so that is what we're talking about. Jerk is given by first derivative of acceleration or second derivative of velocity or the third derivative of displacement function. Clear? How we get this? I just explained using the graph. Whenever that chord moves to the tangent, how do you do that? By making the time frame to an instant time, okay, an instantaneous condition. Then it becomes what? V instantaneous. Okay, then the concept of derivative comes back, because dy by dx actually represents what? Your first derivative is nothing but your V instantaneous in this case, or in nothing but slope of tangent. Slope of tangent. So they have the same meaning. Slope of tangent, first derivative, V instantaneous has the same meaning if you take the curve of dt, okay, distance or displacement by time graph. Okay, clear, right? Not confusing. Okay, let's move on then. Next up, first question. I know this is just a rapid revision session, but I wanted to do a question over here as well. So this question let's solve. The displacement function s of a moving particle at time t is given by this. What are they asking? find its acceleration. Let's do it. A is nothing but d square s upon dt square when velocity is 0. We'll see once we differentiate it, if it has a time constant in it, we'll look for finding the velocity over there. But since we don't have that, since we won't use this actually, we'll see that second derivative of this will make it free from any variable. 5 will become what? First derivative will be what? First derivative will be what? You will have over here ds by dt, right? That's how you find the second derivative. So d by dt of the first derivative, excuse me, check here, you will have here 0 plus 20 minus 4t, and differentiate this, you will get what? Simply minus 4, because 20 will be 0 again, minus 4t will become minus 4. So minus 4 units, option B is correct. Option B is correct. Please check, guys. Okay, so question number 1, the answer is minus 4 units. If it is in meter and second SI units, it will become minus 4 meter per second square. Basically it is retardation. There is a negative acceleration over here. Okay, so this is clear. Question number 1 is clear, right? Let's move on then. Now we have the case of increasing decreasing function. So again we have two different things. One is increasing function, one is strictly increasing function. There's a difference. Okay, so whenever we see in this case, there is no equality over here, right? Do we don't have equality over here. Please check. We don't have greater than equal to, greater than equal to. Whenever the greater than equal to sign is missing, it represents your strictly increasing or strictly decreasing case. In this case also, please check, there is no less than equal to sign. There is no less than equal to sign. Now what it implies, basically I'll show you from the graph. So increasing function represents something like this. Increasing can be constant for some time, again goes back to increasing. So basically this is non-decreasing. Increasing function is something which is can be written as non-decreasing or non-decreasing. This is the first case. Now second case, if you remember, is strictly increasing function. Strictly increasing function. Now this is something different. You will not have the equal to case. This will be always increasing in nature. Means if you keep increasing the x value, y is always going up, up, up. Okay, so this is your strictly increasing case, and this is your non-decreasing or increasing function. Similarly, so what it basically implies that if you take x1, right, and if you take x2, what happens here? F of x2 will be more than f of x1, but can be equal also. If I take here, if I take these 2 points, even though we have x1 and x2 different, even though we have 2 different points, let's call this to be point A and B, f of A and f of B are equal. So we have B greater than A, but f of A is equal to f of B. That's what it means to be increasing function. But in the case of strictly increasing function, any 2 points you take, let's say this is my A and this is B, f of B will always be more than f of A whenever you have B is more than A. If B is more than A, f of B will always be more than f of A. This is the example of strictly increasing. Let's see the other two. Third one is decreasing function. This is also called as non-increasing function. I'll show you from the graph. So it keeps coming down. This is your non-decreasing also. Non-decreasing function. Okay, check here. So even though over here we have A and B, your value of A is value of B is more than A. Value of B is more than A, but f of A is equal to f of B. And in this case it's true, right? If I take this as value, let's say x2, and this is x1, okay, I have x2 more than x1, but f of x1 is more than f of x2. It's reverse actually. Okay, only in this plane case where you have a straight line parallel to x-axis, you'll have equal to cases over here. Otherwise, if I take this point as x2 and this is x1, this point is x1, then x2 is more than x1 even though f of x1 is actually just opposite, more than x2, f of x2 actually. This is the case of decreasing function or non-increasing function. Okay, sorry, I wrote here non-decreasing, my bad. This is non-increasing. Okay, this is non-increasing. It's not increasing, it is simply decreasing function. The fourth case is strictly decreasing. The fourth case is strictly decreasing function. In that, what will happen? There will be a straight drop. If I take this to be my point x1 and this is to be x2, even though x2 is more than x1, f of x2 is less than f of x1. F of x1. Please check. So even though x2 here is more than x1, f of x2 is less than x1 because it is going to be decreasing in nature. As we move along x-axis, y-axis values comes down. Okay, so these are the four cases that I have explained over here with the help of statements as well. So graph, whatever written over here, same thing I have explained in the graphical format. I hope this is clear, guys. Okay, this is rapid revision. Of course, class notes are very important. So all of you all know that WhatsApp channel is there. All the class notes are uploaded there, so please join. If you have not joined it, if you have joined, good for you. You can download the class notes right away, and the drive access is given there. Please download from there and revise these notes. Okay, so increasing decreasing function is over. So far we have covered two concepts. First one, rate of change of quantities. Second one, increasing decreasing function. Okay, now how do we find this? What is the method to find the increasing decreasing function? The first method is first derivative test. First derivative test for finding increasing decreasing function, very simple. If derivative is positive, it is increasing in nature. If derivative is negative, it is decreasing in nature. As simple as that. So in that interval x, for all the value of x in that interval a comma b, if you can find the derivative value as positive, it's going to be what? Is going to be increasing in nature. Otherwise it's going to be, if it is less than, decreasing in nature. If it is 0, then it will be a constant function. It will be a constant function. Please check, guys. So very simple, nothing big deal about this. Now this is about working rule to find the interval where it is increasing decreasing. Okay, so previous one was when the interval is given to you, you find whether it is increasing decreasing or not. In this case, we will not find only increasing decreasing, we will also find the interval where it is increasing decreasing. Okay, so it's okay. Let's get back to the question. So this is going to be the working rule to find out the interval in which the function is increasing or decreasing. Step remains same, find the derivative first. Step 1 is to find the derivative. Step 2 is to find the critical point. So first we'll find the derivative. What you get over here, 10 is 0, this is minus 6, this is minus 4x. This is the step number 1. Step number 2 is to find the critical point. How do you do that? By putting derivative as 0. Put here derivative as 0, you get minus 6 minus 4x. Okay, so you'll have here minus 4x minus 6 equal to 0. From here you get x value as minus 3 by 2. X value as minus, if you bring this over here, get 4x equals to minus 6, right? Alright, okay, 1 second, guys. I'll just show you, because I want to make the coefficient of x positive. That's very important. I want to make the coefficient of x positive. 1 second. So please check. I'll move on this side. I get 4x plus 6 equals to 0. So I get x equals to minus 3 by 2. 6 will go over there, right? It will become minus 3 by 2. Now I draw the number line. What we have over here, we have this as minus 3 by 2. That's my last step. Now check, the coefficient of x is positive or negative. It is positive, so put here plus sign. The right hand side, this side will be negative because the factor has only one power. Power is odd, right? So we are gonna keep the sign change. This is infinity, this is negative infinity. Wherever it is plus means, what is the meaning of plus? Means any value you take after the minus 3 by 2, it will become positive. Check here. Take 1, take 0, it will become 6. and over here take minus 2, it will become minus 8 plus 6 will be minus 2. Okay, so basically on the right side of the value minus 3 by 2, the derivative is coming as positive. Here the f dash of x is positive and here the f dash of x is negative. Now you can find the interval. F dash of x is positive in the interval, what is it? Minus 3 by 2 to infinity, open, this is the interval, right? So basically fx is increasing in the interval x belongs to minus 3 by 2 to infinity. Okay, and f dash of x, this is the first point. Second point here, f dash of x is less than 0 in the interval negative infinity to minus 3 by 2. Okay, so what I get, f of x is decreasing in the interval x belongs to this minus 3 by 2. That's your answer. Both part is covered over here. When derivative is positive, fx is increasing in nature in that interval, and when derivative is negative, fx is decreasing in that interval. From the number line we can observe that. Okay, so clearly I hope how to find the intervals where the given function is increasing, decreasing is clear. Okay, this is the working rule. So I've taken an example to help you understand that. Let's move on. Next we have the last concept of maxima, minima. Again, all of this is there, but I'll help you understand this with the help of a graph. Okay, so maxima is usually of two types, something called as local maxima or global maxima. Global means in the entire domain you will reach a highest value. I'll show you the example. For example, if I take the graph like this, check this out. So how many maxima you have? You have number 1, number 2, number 3, number 4. Okay, all these 4 are local maxima, but only one, this one will be your absolute or global maxima. So basically when you have more than one critical points, you look to compare which has the highest of all the 4. Let's say you have total of 4 or 5 critical points. In that 3 are maximum values and the other 2 are minimum values. Okay, how do you find that? I'll tell you that, don't worry about this. We have a approach called as second derivative test. With help of that we can easily identify which is the local maxima and local minima point. Okay, whereas all the points are called as point of extremas. So whether it is point of maxima or point of minima, it is always called as generally point of extremas. The word is point of extremas, in that both maxima and minima comes. Okay, clear? So we have over here 1, 2, 3, 4, 5, 6, 7. 7 point of extremas where 4 are the maxima and 1, 2, 3 are the minima. 3 are the point of minima. Okay, total 7 extremas are there. Check this out. 5, 6 and 7 extremas are there where the top 4 are maxima and the bottom 3 are your minimas. Okay, now again, which is the global minima? The smallest one, this is the smallest one, this will be your global minima, means smallest of all the small value is called as global minima, and largest of all the larger value is called as global maxima. So clear what is global maxima, what is global minima or absolute? Global is again a different name for absolute, it's the same thing. Usually in your textbook they use absolute maxima, it's the same thing. Okay, this is your absolute maxima. Okay, and this is your absolute minima. Clear? Actually your local maxima in this case are 0.1, 2, 3, 4. 0.1, 0.2, 0.3 and 4 are local maxima, and local minimas here are 5, 6 and 7. So 5, 6, 7 are your local minimas, and local maximas are 1, 2, 3, 4. Okay, in which global or absolute maxima is 4 and absolute minima is 3. Okay, now this is the understanding of maxima, minima, local maxima, local minima, global maxima, global minima. Now we'll get back to original definition of when can we call a given point, a critical point, a maxima. Okay, let me explain you that. Just quickly, 1 minute it will take. So whenever you have a graph like this, a function like this, when at this point, at the point x equals to a, in the neighborhood of the point x equals to a, let's call this to be b and c. In the neighborhood of the point x equals to a, let's call this to be point b and c, f of a is more than f of b and is more than f of c. Means f of a is the largest, okay? F of a is the largest in the neighborhood of the point A. What's the neighborhood means? Neighborhood of the point means, if I take a small value delta, okay? So delta minus a to delta plus a. This is called as neighborhood. Means very close vicinity, in the very close vicinity of the point A. Very close. When I say close, means you can't even look at it with the naked eye. That's close, okay? I'm talking about very close. In the close vicinity of the point A, not this far, very close actually, just to show you I've taken a very far distance, okay? But in a very close vicinity, if you check here, all these values will be smaller than the value at the of the function at the point A. Then the point A becomes your point of local maxima. Local maxima, okay? So f of a will be more than f of b and f of c. Whereas in the case of local minima, just opposite happens. Just opposite happens. So graph will be like a pole, okay? So if this is point A, right, and this is b and c, what will happen? F of a will be less than f of b and f of a will be less than f of c. So in the neighborhood of the point A, f of a will be the least, then it becomes local minima. This will become local minima. Clear? I hope you are able to understand that, even though my handwriting is not looking very perfect, but I hope the concepts are getting easily cleared, okay? So local maxima, local minima, absolute maxima, absolute minima, and how do we define maxima minima? This is the definition, okay? Same thing written over here. F of a is more than f of x. What is x? X belongs in the interval b to c, or a to b in this case, whatever is the interval, okay? So in this case we have taken the interval as b to c. So in the interval b to c, all x values, f of a is the largest, it becomes maximum. When it is least, it becomes minimum. Again, what is I? The interval b to c, what I took in the graph, in the figure actually, not the graph. Is it clear? Same thing I've explained over there. Local maxima means in the neighborhood of that particular point, it will be the largest, and local minima means in the neighborhood of the point, it will be minimum. So local minimum. Clear or not? Please check, guys. Clear or not? Okay. Now after this we have to learn two things. First derivative test to find maximum minima, and second derivative test to find maximum minima, and the session will be over. Please check. Let's move on. Yes. Yeah. Now what we have is first derivative test. Again, steps are written over here, but let me explain it to you first. Okay. Let me explain it to you first. So let me talk about local maxima first. We are trying to identify and learn first derivative test for local maxima. Local maxima curve look like this, if you remember. Local maxima. So what happens is, when you find derivative, first derivative means what? First derivative means dy by dx. This much I have explained you today only in this session. First derivative is same as dy by dx, also called as slope of the tangent, okay? Super, sir. So if I consider this point at the point x equals to a, if I go left of the point A, left of the point A, left of the point A is these points here, here, here. Let me draw a tangent over here on the left side. Tell me, for this tangent, if I find the slope, will be positive or negative? This slope will be positive or negative? It will be positive. This slope will be positive. What it implies? It means dy by dx is positive here. What it means? It means y dash or f dash of x is more than 0. same thing, they are the same thing. dy by dx is positive, y dash is more than 0, f dash of x is more than 0. They are exactly same thing on the left hand side. Okay, now let's look at the right hand side of the point A. I'll draw the tangent again. This is the right hand side. Draw the slope, find the slope of this. You'll get an obtuse angle, right? If you find the angle theta, you'll get obtuse angle here or not? Yes, you are. Please check. From the counterclockwise direction of the x-axis, you're getting obtuse angle. For this, whatever is the angle, you'll get slope will be negative. Slope will be negative. It means what? Slope is nothing but dy by dx will be negative. What it means? It means your y dash, y dash or f dash of x is negative. Your f dash of x is less than 0. Okay, so basic conclusion is, if your slope changes sign from plus to minus, please check. From left to right, if you are moving, here it was plus, here it was minus. When the slope changes sign from plus to minus, what happens? It is point of local maxima, or basically your derivative changes sign from plus to minus, then the point is local maxima. That's it. Whenever the derivative, the slope, whatever you wanna call, slope or derivative, changes sign from plus to minus, it is point of local maxima. Then the point will become x equal to a will become the point of local maxima. Let me know if it makes sense to all of you in the comment section right now. Okay, I want to know whether you understood this concept or not. It is very, very important. Please check, guys. Clear? Okay, so local maxima is clear. Please check. F dash a should be 0 and f dash of x changes sign from positive to negative as x increases through a. This is called as local maximum value, local maxima. Now is local minima. Same thing, reverse bowl. X equals to a. Tangent time. Draw tangent like this and draw tangent like this. For this, tangent is positive, it's acute angle. Slope is positive. Slope means dy by dx is positive. Over here, if you draw an angle over here, this will be a obtuse angle. So over here, what you get? You get slope is negative. So you have dy by dx is negative. Dy by dx is negative. So whenever slope or basically dy by dx changes sign from minus to plus, then what will happen? Then the point is local minima. Got it? That's the conclusion. That's our conclusion for first derivative test. First derivative test. That's our conclusion. dy by dx changes signs from negative to positive is called as point of local minima. Have a look. Clearly visible. Okay. Minus to plus, local minima. Okay. No change means, okay, no change, what will happen? It will be called as point of inflection. I can show you that. So basically like this. Check here. This will be your point of inflection where the slope does not change the sign, but concavity changes. Here concave down is a concave up, here concave down. So whenever you have concavity change, it's called as point of inflection. Okay. whenever you have concavity changing, nature of concavity changes from concave up to concave down, that point will become point of inflection. So please check, guys. Clear? All this point is clear here. First derivative test. This graph is clear for local maxima and local minima. Point of inflection also should be clear. This is your point of inflection. Inflection point. Okay, clear, sir? All right. Now again, some of you might think that, sir, this is too lengthy. Yes, it is actually. But for some questions, no, it's difficult to apply second derivative test, which is relatively simpler. But let's say you have a complex quotient rule applied, then difficult to find second derivative again. For some student it will be difficult. Then what happens? Then the first derivative plays a big role. Okay, but second derivative test is simply easier and recommended. What is going to be in this case? Find the first derivative, put it equal to 0. What are you gonna find? You're gonna find your critical point from here. This step is to find what? This step is to find critical point. Do not worry. When I'm solving questions, whether it is 1 marker, 2 marker, whatever it is, I'll teach you how to find critical point. Okay, so critical point, once you find, check whether at that point second derivative is positive or negative. I'll repeat. First derivative you found, put it equal to 0. You find now whether the second derivative at that critical point is less than 0 or more than 0. If it is less than 0, it is local maxima. If second derivative is more than 0, it is local minima. Okay, local minima. And in this case, you have to use the first derivative. Please check. Okay, so this is clear. Second derivative is positive at that critical point, local minima. Negative at the critical point, local maxima. And this completes our session on the rapid revision of the concepts coming for your PU2 midterm in the chapter AOD. So with this I can end the session, right? Any other feedback you have, let me know in the comment section. Right now this is it for the session. I'll see you again very soon. Till then, take care. Bye bye.